Hi all, welcome to week 6 tutorial for COMP9417. Hope you all had a great break in the flexibility week. Today we will be talking about neural networks. It's a very exciting area within machine learning. And when you have the, I suppose, more sophisticated neural networks, emphasis there on network rather than just say perceptron, then we often refer to it as deep learning. Very exciting area. So what we'll be talking about is I'll give you a bit of an introduction. I'll talk about the basic building block of the neural network, the neuron, otherwise known as the perceptron, within the context of machine learning. I'll talk a bit about learning in regards to the perceptron as well as the neural networks, how they learn, or in other words, how they fit to the data. We'll talk, and one of the techniques there is your back propagation. And then some thoughts on, I suppose, more sophisticated neural networks or specialized ones, convolutional neural networks, and might touch on the recurrent neural networks, different forms of your neural networks. So let's get started. So a lot of the recent advancements in neural networks, a lot of the recent excitement in machine learning has been driven by neural networks. They're quite good. Some depending on which kind of use, they're quite good. In terms of computer vision, so we're probably saying that facial/image recognition has gotten quite good these days. And natural language processing, that is dealing with just free text, speech, and also some AI game playing agents. Like you might have heard of AlphaGo, which uses I can't remember the exact structure, but there's some neural networks there, alongside a whole bunch of other sorts of things in there as well. What else did I have in that AlphaGo? I think they have some sort of what is it called? Some alpha beta pruning, and what was it called? They use some sort of Monte Carlo simulations in there as well. Monte Carlo tree simulations in there as well. But a lot of that is but there is also a neural network inside the AlphaGo AI. There's a whole bunch of things in there that thing's quite complicated. So neural networks have actually been around for quite a while now. The theory has been around for decades, but it's only recently that we had the data and computing power and needed to properly harness them, right? So from the from the get-go, when this concept was first sort of thought of, they were doing things, a bit manually, switches, mechanical sort of switches and circuitry, rather than, of course, now we have, the micro transistors or, our microchips that we're somewhat familiar with now. The neural networks, as the name suggests, it's inspired by the human brain, which we'll see in a moment. So neural networks are highly parallel, and as you may be aware or may not be aware, in practice, often people will use GPUs, graphics processing unit, or video card, rather than a CPU, because they're often quite a bit better with parallel processing, when compared to just your regular CPUs or central processing units. So let's talk about the basic building block of your neural network, and this would be the perceptron. So on the left here we have a diagram of a I'm not a biologist, nor am I a doctor, so I can't talk too much to this, but this is a diagram of the neuron, right? And this is, I suppose, the inspired machine learning version of the neuron, and we can sort of see analogies. So you can see, how we can see how the perceptron in machine learning land has taken inspiration from your biological neuron. So your biological neuron in your brain, you have is it millions or billions? I don't even know. I don't know which order it is, but it's either millions or billions. There's many of these inside your brain. It's highly parallel. They're all linked, or not all, but a lot of them are linked to a lot of other neurons. So here, you have these dendrites which are linked to other neurons and possibly other cells in the body, which you can kind of think of as the inputs, right? And it goes along this axon here, right? And if the electrical impulse from all these guys is from all the inputs is strong enough, then a pulse will go through and it'll go along to the other. It'll go along and it'll go along these connections to other neurons, right? So hopefully you can kind of see the inspiration there. So in our artificial neural network, the inputs would be the features, right? At least in the perceptron. When we look at the artificial neural network, this will be possibly these inputs will be will be from another neuron. But for the time being, we're talking about the perceptron, which is just the one neuron in the neural network. So if you just have the one, the inputs they should just be the features. So the analogy is, the features will come in here, right? Okay, and it will go through the axon. So the features will come in here on the left, right? And then what you'll do is you'll take the, I suppose, the sum product. So there's a couple of different ways to think about it. So this guy here, so you can think of it as something like this. Right? The sum product of all your weights as well as all your features, right? You can also think of it as the dot product, as a dot product of your features or your inputs, as well as your weights for each of these inputs, right? And then there'll be an activation function, something we'll go through a bit later, but the activation function for now you can think of it as, it's a function which we apply to the sum product of the inputs and the weights coming in, right? And so you have your features or your inputs coming in, analogous to, you have electrical impulses coming from other neurons into this neuron here, right? And then and then all these inputs are aggregated. You take the sum product here, so all these inputs here are aggregated, and then if the electrical impulse is strong enough, it will output, right? So here, the electrical impulse will only fire if, whatever's coming in here is strong enough. So what will happen is, all these features will come in, and if the sum product, after feeding through the activation function, if it's strong enough, possibly, and depending on how you set up the perceptron, it could be -1 +1, or it could be something like 0 1, depending on how you want to code it, or it could be something else. But let's keep it simple and just think of it as possibly a classification for the time being. So the inputs go in, right? You aggregate the inputs, you apply some sort of activation function, right? And then the output becomes, something like this, 0 or 1. Of course, it could be a probability maybe later on. It may not just be 0 1, but and it depends on what activation function you have, as well as you can actually have multiple outputs as well. It doesn't have to be just the one. But let's just to keep it simple, we'll just have features, activation function, and just the output. Let's just think of it as 0 1 right now. Just start thinking about classification in the back of your head, just to wrap your head around this. Okay. So I touched on the activation function on the previous slide. So here we'll see it in a little more detail. So this is the perceptron from the previous slide, and again, this is what we call the input layer. These are the inputs, and this is the input layer. All right, and we call them layers because later on you might have many layers of neurons, but this is just a perceptron, so it's just, there's no layers. Well, there are layers. It's just the one neuron. Okay. And again, you have your activation coming in. So this is just your sum product of your weights and your inputs. And here's the activation function I was talking about momentarily, right? So there's quite a few activation functions we can sort of choose from, but the simpler one, which the binary step function. Maybe I'll just copy this over. But one of the simpler ones, which is in this example, is this one here. Maybe I'll just leave it here just so we have a bit of a flavor. This little step function that we have here. Okay, this is the activation function being used in this example. So that's this one here. Now, of course, there is a bit of a shift in the sense that, I mean, this one here it looks to be outputting either +1 or -1, and this one appears to be 1 or 0, but you can define it to be +1 -1 1 or 0. It doesn't really matter too much. It depends on your application, but this is some kind of step function, right? So hopefully you can see what's happening here, right? In this step function, what is happening is it is taking in this is the input, right? That goes into this activation function here. So what's that? This is the wx dot, right? That goes into there, and the output, sorry, what that is. So the input, is, real, or I should probably say the domain is real, and then the range coming out of here is just, it's 0, 1. I just realized I made a mistake in the notation. This would probably be a set rather than a range. Okay. So, so this inputs come in and you aggregate it. They can be real, but you feed it through some kind of function and it forces it to either be 0 or 1, or I suppose in this case it's +1, -1. Again, it's a bit of an arbitrary choice as to which one you want to do it, and then that will give us the output or our prediction. So hopefully you're kind of piecing together how this perceptron can be used as a classification algorithm within the context of machine learning. Okay, so we can actually just use this as a linear classifier, as we say here. So we've seen linear classifiers before, but the linear classifier can actually be viewed as a perceptron, right? And here it is sitting here, right? So you have your classification task, and you might, and in this case you only have your two. In this case you only have your two features, right? You feed in your two features, you aggregate it together, you feed it through the activation function, and I suppose if you created a good classifier, it's going to either classify it as positive or negative, and that'll be your prediction, right? So you can see here that sum there, that's this thing here, that's that guy there, that's that guy there, right? You put it through and you just have some sort of, I suppose you can think of this as your classification rule. And a bit of nomenclature, a bit of terminology. We've already seen these sort of things before, but this could be any sort of classification problem. So you can think of it as in our previous weeks I've spoken of the fish species classification example, whether it is salmon or sea bass. So possibly x1 could be say fish length, and then x2 could be fish weight, and maybe this side is, I don't know, say salmon or something. I don't know too much about fish, and maybe this is sea bass. Some sort of classification problem. And of course you can generalize this to an arbitrary number of dimensions. It doesn't just have to be 2 dimensions or 2 features. Cool. All right. So the next thing I want to talk about is what's called the Perceptron learning algorithm. So, this is all well and good, right? And, we've got this Perceptron here that can, this one here, it's doing quite well. I've got 6 training examples, and it's perfectly classifying them all. There's no training error. So this is all well and good, but then the question is, how do we find this line, right? And bear in mind, this line here is made up of these weights, right? This line is made up of these weights. So what's the best way to sort of because effectively this line here, it's be described by plus w1x1 plus w2x2. This line will be characterized by this equation here, and of course you can rearrange it so that you have, which is equivalent to, say, x2 there, and then you have I guess it's negative minus w1x1, right, divided by w2. You can rearrange it to arrive at this, but effectively this activation here, right, that is that line here, right, and then your decision rule is if this activation is greater than 0, then you say it's positive, or in this case greater or equal to 0, you say it's positive class. If the activation is negative, then you say it's in the negative class, or the 0 class here, which is just your BAS, right? So you can characterize this decision boundary as a straight line, and like this in your general form, or you can change it to y equals mx plus b form if you like, something like this. Okay, yeah. So so over here, so how do we find that line? So there's so what we have is this perceptron learning algorithm. So the way I want you to think about this perceptron learning algorithm is you go through each of the data points, right? And every time there's a misclassification, you bump up or down the weights depending on how you misclassified it, right? If it was if you say classified it as positive when it was meant to be negative, then you should probably bump down the weights because it was too high. If you classified it as negative when it should have been positive, you probably should bump up the weights a little because it was a bit too low, right? And of course, if it's fine, yeah, you just leave it. There's no need to nudge or bump the weights for that particular training example. So that's a general idea behind the perceptron learning algorithm. There's a few considerations. The first one is the learning rate. And so the learning rate effectively is as you cycle through all your training observations and you make bumps and nudges depending on whether, I suppose, depending on how you misclassified it, right? The eta determines how much of a bump or nudge you will do, right? And you might choose something like 0.1, 0.01, 0.25, say, depending on, depending on the data, right? There's a few considerations. You don't want the learning rate to be too low because it's just going to take far too long to converge. On the flip side, if it's far too high, then you'll miss the global optimum. So I mean, you have say problem one. Definitely, you've probably seen this before. Let's say you're doing some sort of gradient descent of sorts, and you're trying to find the global minimum. And if the eta is too low, then you're sort of just it's taking too long. And you don't end up converging. You don't end up converging on the global minimum. Now, of course, there is this other problem, right? So say, for example, if you have learning rate which is too high, you might just constantly just bounce. You might just constantly just bounce around and just, you just miss you miss the global optimum, in this case, a global minimum. So there's two things to sort of consider here: too high, too low, and then this will be considered a hyperparameter. This little eta here, right? And it's something you'll tune, something you'll define before you start learning, and then you can play around with that to find out what your best hyperparameter, what your best learning rate is for that specific training data hyperparameter. Right. Okay. Cool. So now with the training algorithm, you just recall the training rule, right? So you'd have, if your activation is greater than or equals 0, then remember your y hat is 1, your prediction is 1. If the activation is less than 0, then your y hat, you set to, so let's say -1 in this case, right? Now, if it was some sort of misclassification, in this case, like y is this, and then we actually, we have y hat is equal to -1, and of course the other side of y hat is equal to +1, right? So in the first, when it's misclassified, you have one of two things happening. Number one, you classified negative when it should have been positive. So actually, this was too small. So we want to increase our weights. We want to bump our weights. The opposite thing can happen. You predicted that it was positive, but it should be negative. So the weights, the activation is too it's too big. You want to decrease the weights, right? So how do we express this into some kind of rule? Let's have a look at this bit of pseudocode here and work out what exactly is going on. So you have training data capital D, right, and a learning rate eta. Okay, your W is the weight vector. So you initialize it all to 0 for the time being. In practice, typically you'd initialize the weights to something random and something small. You don't want to be sort of stuck at 0. Okay, and then we have this little marker, this little flag here saying converge is false. Okay, so we keep cycling through all the data until we converge, right? Until we converge at some sort of solution. Okay, so right, so we go through it. We reset the converge flag to true, and then you cycle through all the data from 1 all the way to the cardinality of D. So 1 to n, say, cycle through all the data, right? Now, what is it saying here? So So this here is basically when there's a misclassification. When there's a misclassification, right? This is going to be negative, and let's have a think about why, right? So, okay, yeah, that's exactly it. So basically, w dot x, that's y hat, right? That's a prediction, right? Now, if y hat equals to y, then actually, this expression here, I guess y y hat will be it's going to be 1, isn't it? Sorry, it's going to be, do you know if it's 0 times 0? Oh no, it's minus 1. Yeah, sorry, it's going to be 1 because they're both either plus or minus 1, right? It's only when y hat is not equal to y hat, then what happens is y times y hat is going to be equal to negative 1. In other words, it is negative. So this only kicks in when there's a misclassification. So you cycle through all the data, and when there's a misclassification, right, then you bump the weights, then you change the weights. But only do this if there's a misclassification, right? And what you do is you bump it up by the learning rate times, I guess this will give you the sort of directionality, right? So if you misclassify it and it should have been positive, then this will be positive, and you'll positively bump up the weights. And if you misclassified it and y should be negative, then you'd bump it down, sort of nudge down the weights. So you change the weights here, and then because you change the weights, you set it to false, right? So convergence would happen if you cycle through all the data and you don't enter this this if statement here, this inner if statement here, and you don't change your weights. So that's when you converge there, right? So to summarize, your perceptron learning algorithm is basically cycling through all the data, right, one by one, and bumping the weights up and down if there is a misclassification, and you keep doing this until you don't need to bump the data up or down anymore. In other words, it is converged and everything is perfectly been classified. Of course, that might be wishful thinking, that you have an algorithm that you can perfectly classify everything, and it is, and we'll talk about that in a little moment in terms of the considerations about the perceptron learning algorithm, in that can only handle perfectly linearly separable data. So it's only if you can actually create a classifier that is perfect, that everything is classified correctly, because otherwise this loop is going to continue. You could argue that possibly you set a cap on the number of iterations, but there's other things later on that we'll see which might be used more often. So here's the other alternative. Here's the other alternative to your perceptron learning algorithm. It's using good old gradient descent, which hopefully we are somewhat familiar with now. I hope. Right. So in a nutshell, what gradient descent is you want to. So if this curved surface here, let's say the z-axis or this vertical axis here. Let's say this is some sort of cost function. Say the sum square error, and it's something we want to minimize. Weight 1 applies to feature 1. Weight 0, that's a bias term, but let's say there's two parameters, there's two weights we can tweak, right? And our goal is we want to get to the bottom. Is that the bottom? Our goal is we want to get to the bottom here, right? This is the global minimum, right? We want to get there. Now, gradient descent, what it does is it tries to, let's say this is our initial guess, or this is our initial sort of weights, right? Well, okay, let's find the direction and let's step in the direction of steepest descent, right? Let's move, and and we'll talk about how to calculate it, but let's just say for time being we know which direction is of steepest descent, and we take a step that way, and we keep doing this and hopefully land on the global minimum, right? So we can consider it weight by weight. I know this here is a vector. This is a vector that points in the direction, but you can also consider it component wise. Instead of the gradient vector, you can look at each one individually. I suppose the gradient vector is actually composed of individual component wise the partial derivatives anyways. Okay, so let's have a look at this, what's happening here. So if we consider each sort of weight, let's say weight 0, we want to nudge weight 0 by, and why is it negative? Because gradient is the direction of ascent, right? Now, this is something we want to minimize. So we want to step away. The gradient vector points towards the direction of increasing slope, but we're trying to minimize this. We're descending. It's not gradient ascent, it's gradient descent. Hence the negative. So we want to go in the opposite direction of the direction of steepest ascent. And of course, we apply our eta here, which is the learning rate, which you can tweak. Okay, so we can think of like weight by weight, or you do it all at once. Same thing. So you have your weight vector. In this case, it'll be weight. In this case, it'll be a W0. W0 and W1, right? Okay. Okay. And then you just bump the entire weight vector by you move it in the opposite direction of the direction of steepest ascent. Okay. So this is all well and good. We can make it a bit more concrete. Now, the weight function is with respect to some j, which is the cost function. Now typically, and in this example, we'll assume the sum square error. So what you can do is you can calculate the partial derivative. You can calculate the partial derivative with respect to the sum square error, and it looks like this. You basically sum up through all your data and the difference between your predicted value as well as the actual and then the actual feature value, right? And that is your partial derivative, which you found using just a bit of calculus, right? And of course, like in your Perceptron learning rule, your typical considerations for your learning rate applies here as well. You don't want to be too slow because you just take ages and you may never reach your minimum. You don't want to be too fast because you may bounce around too much. You may skip over some kind of global minimum. And the other thing is as well, if it's too small, you might also get stuck in some sort of valley. So when I say valley, I mean like, say this is some cost function j, and this is, let's say you're only considering one weight, right? You may get stuck in some cost. You may get stuck here because you didn't move enough and you're sort of stuck there. Now, of course, one way to get around that is you do random restarts. So you might then use random restarts. Now, when I say random restarts, what I mean is you'll reinitialize all your weights to something and then perform your gradient descent again. So your initial attempt might be here. This might be attempt 1. Right, and then your second attempt might be here. This might be attempt 2, and then you just take the minimum of all your attempts, and you have it. Cool. The next thing to consider is consideration of the Perceptron learning rule versus gradient descent. Now, gradient descent. So sum square, and when you're trying to minimize sum square, one of the great things is that it's a convex minimization problem. Now, when I say convex, I mean it looks something like this. E.g., the local minimum is also the global minimum. So we don't have to worry about being stuck in any valleys or anything. If you get to a minimum, it's a global minimum. It's just convex, some kind of convex the whole way around, which gives us which is nice, because when it says always works, it means we'll always find the global minimum rather than just the local minimum, right? Now, the Perceptron learning rule is guaranteed to succeed. It's only if the training examples are linearly separable. Now, by linearly separable, what we mean is that something like this. Let's say you have training example, training example, training example. this is linearly separable, right? This is linearly separable because you can draw a straight line between them and perfectly divide the two classes. Now, this example, which I'm going to set up here, is not linearly separable. You cannot draw, possibly the best line we can do is here, but you can't draw a line which will perfectly separate the two classes. So this is not linearly separable. Okay, right. Right. So that's one of the downsides of the perceptron training rule. Now, using gradient descent, it's fine with this. You know, it will still converge to a set of weights, which will minimize the sum square error, and it can deal with the cases when it's not perfectly linearly separable, and perhaps maybe this is noise, maybe there's a bit of noise in the data, right? So there's a few different types of gradient descent I want to discuss. There is your batch gradient descent. Now, batch gradient descent, why is it called batch? It just means the whole data set. It just means the whole data set. So what you'll do is you'll compute the gradient vector on the entire data set like this, and then you'll update the weight vector, all at once using the gradient of the entire data set, right? Okay, and of course, using this is the error, the sum square error. This error here is sum square error. Oops. As defined by this, it's the observed versus, I suppose, the predicted value, and you square it and you take the sum. The half there is just for mathematical convenience. So when you take the derivative, they just cancel each other out and become a 1. And of course, you can work out the partial derivative for this. So the gradient is basically made up of all the partial derivatives. It will look something like this if you differentiate through. You apply the chain rule and apply it through, you get something like that. Now, yes, so then that's the batch gradient descent. The other one is incremental gradient descent. So instead of this one, you only update the weights. In the batch gradient descent, you use the entire data set and then you update the weights. Now, incremental gradient descent, it'll be at every single data point, you'll be updating the weights. Okay. Then you have, and that's this here. So rather than this is one data point, right? Just little case, small case d. It's one data point rather than the whole data point. Now you have your stochastic gradient descent as well, and it's like incremental gradient descent, except you just pick a data point at random and you'll sort of cycle through. Okay. Now let's talk about neural networks. So far we've only discussed like the single neuron. We haven't discussed a network of neurons, or in other words, a neural network. So here you can see, so each one of these guys is actually a perceptron. Each one of these circles is some kind of perceptron. There's an input and some sort of output, right? These are all perceptrons in here, and they're arranged in layers. So you have your input layer, which possibly your features are coming in. Your input layer where possibly your features are coming in, right? And then you feed it through the first layer, and then there'll be little outputs which will feed through the second layer, and then finally the output layer, which is where your predictions will be spat out. Okay, so a neural network has at least one hidden layer. So this is a neural network with 2 hidden layers, but to go from perceptron to a neural network, you need to have at least one hidden layer in between the input and the output layer. So with the perceptron, you just have the input layer and the output layer. You don't have the hidden layer. Okay. The good thing about perceptron, you remember how when we saw it, it's basically a linear classifier, which means that it really only works perfectly with only works well with linearly separable data. Now, when you add all these hidden layers here, it adds a lot of flexibility to your neurons, and you can handle nonlinear data and very, very complicated types of data. So here's another schematic of your neural network. You have your features coming in, and then they'll be multiplied by all these weights here, right? And then it will feed into, like, say here. So here, the input is the input layer, right? And you apply weights to all of them, and then there'll be some kind of output, right? And that output comes here, right? And it feeds into here. Now the output layer takes in 3 inputs, and a weight will be applied to each of them, and then they'll feed into its own activation function, and then that will spit out the output, right? So each one of these little guys is a perceptron, and they'll have its own sort of activation function, and each one of these red lines will have its own weight, the strength of the neural connections. So activation functions. So there's quite a few. There's quite a few activation functions. So activation function is what you apply to, I suppose, the weight and the input of the previous layer, right? And typically it's real. The input, the domain coming in is real, and the output you often bound it using one of these activation functions, right? So the one we've seen so far is the binary step function. So this goes from say your real to just 0, 1. Okay, I mean this is real to real, and this one goes from real to 0, 1, your sigmoid activation function, which we'll see in a bit. It's got some nice mathematical properties involving its derivative. And then you have your hyperbolic tan, which I think goes to this. But let me check, I could be wrong. What is the range of hyperbolic tan? Hyperbolic tan. Tan H range. I think it's -1. Yep, -1, 1. Good. Just to be sure. Cool. What do we have next? Backpropagation. Oh, so okay. So yeah. So far we've discussed learning in a neuron, but perhaps a whole other can of worms. To open up a whole other can of worms, and we'd talk about learning. In other words, working out the weights in an artificial neural network. So I'll give you a high-level intuitive explanation here, right? But I do encourage you to go through in the lecture notes. There is a must have closed it in the lecture notes. Currently unavailable. That's must have logged out. Huh. Doesn't seem right. Okay, well, in the lecture notes, I'm not logged in. That's probably why. Here we go. Cool. Okay, so in the lecture notes, they go through backpropagation. They use a chain rule and this and that, and they assume a sigmoid activation function. So I encourage you to go through this, this working out here. But perhaps before you do that, if I provide a bit of motivation and intuition, that might make it a little clearer. Okay, so one thing to note is that backpropagation is gradient descent applied to an artificial neural network in order to learn all the weights, right? The backpropagation, what it is it refers to the way the partial derivatives are calculated. So this is your neural network, right? Now, if you think of your typical learning problem in gradient descent, we want to work out what weights to use, right? Want to work out, what bumps and nudges we need to apply to all these weights in order to minimize the cost function, right? The difference between, say, the predictions and the outputs, right? So we need some way to work out all the gradients. So you'll have a gradient for every single one of these lines here that needs a gradient, and that is a weight, and that needs a partial derivative with you need to find the partial derivative of the loss function with respect to all of these weights, and then you form a gradient vector, and then you nudge the gradient vector, the weight vector by minus the gradient vector, which gives you all the partials. Now, the way we start is, and why is it called backpropagation, is you start at the back of the network, right? And then you propagate, and you start at the back of the network, and you calculate all the partial derivatives, right? And then you propagate it backwards. Now, why do we need to propagate it backwards? It's because we need a chain rule, right? We So when you're looking at this last layer here, all these weights, this cluster, it's reasonably straightforward. All you need is del, the cost function, and then del, that weight, and it's just kind of there at the end. But then you look at the previous ones, right? Now the previous ones, depend on the way on the hidden layers in front of it, right? So for example, this guy here, this weight here, you effectively want del the cost function divided by del this weight. But the way we do this back propagation is we use a chain rule, and we use the partial derivative from here and propagate it back to here and use a chain rule to get the partial derivative here, right? So let me summarize it again. We start by finding the partial derivatives at the back. This is the back of the network, the last hidden layer. This is just a simple partial derivative. And then we go to the layer behind it and we calculate, using the chain rule, the partial derivatives, all this, and you rinse and repeat all the way to the front. And that gives you the partial derivatives for all the weights. And that's the nudge and the bump you need at that iteration. And then you just keep repeating it. And that's your gradient descent in a nutshell. So backpropagation is, it's complicated, not the easiest to understand. Now I highly recommend, again, so understand this motivation, right? I also strongly recommend, there's a really good video on YouTube by 3Blue1Brown, and I've never seen a clearer explanation of how backpropagation works. That's a really good one. Although one thing which will be although one unfortunate thing is the notation is different to this course, obviously, but it is different to this course. And then maybe go through this simple example here, which uses a sigmoid activation function, and there's only a few hidden layers. I think there's only one even. It makes it a lot simpler. Right. Next thing I want to talk about is there's a few, I guess, alterations or extensions, if you will, on the regular neural network. You have what's called your convolutional neural network, which looks something like this. And the way this works, and this is very good for image data, it's very common in image data. This is your normal neural network, and what you notice is that it's what we call fully connected. And what this means is that every layer, and what this means effectively is every previous layer is connected to the layer after. It's all linked up, right? Now the problem with this is this means that it becomes computationally very expensive. Especially when you have image data and the resolution sort of blows up, and you have many hidden layers, right? Let's say you have like a 1024 by 1024 image, so if, say a million pixels, and your input layer is a million, and then and then you have a few hidden layers, and you just multiply it all up. The number of weights just kind of blows up, and it becomes difficult from a computational point of view. So what convolutional neural networks do is use these sort of convolutions, and you consider sort of local features where, two things. Instead of each layer being arranged in like a sort of one-dimensional, like this, it's arranged in a three-dimensional way. So it's sort of like you have, kind of like a picture, right? You have, the two dimensions in the picture, and then this could be, say, your RGB channels, right? Okay, so this could be the x-axis, this could be the y-axis, that could be the RGB channels, right? And then the subsequent layer, right, it's only connected locally, like, so this little box here, this little neuron here is only connected to all these neurons here, right? So you can imagine how, like, being locally connected, the number of weights just decreases a lot, right? And there's a lot of like extra little nuances there, right? You can apply filters, and there's a bunch of other little things here, right? And then there's all these convolutional layers. But interesting thing is, right towards the end, you have all this, and then you plug it back into a fully connected normal neural network, and then you run your normal. After this, you run your normal classification exercise at the end using your fully connected normal, I guess, neural network. So if you are curious about playing around with these neural networks, I encourage you to. Scikit-learn has a really easy API to just fit a multi-layer Perceptron, a basic neural network. You can see a bit of code here. It's quite easy. I'd also recommend Keras. There's quite a few neural network deep learning sort of packages, but Keras is one of the easier ones. And of course, there's COMP9417 at UNSW, which is a great course on neural networks and deep learning. Oh, sorry, I shouldn't wrap up here. I've got to go to the Python notebook. So, anyways, that stuff also applies, but let's move along to the Python Jupyter notebook. So, let me just make this a bit bigger so we can all see. Okay, so what our starting point is, we're going to do a bit of linear classification with your perceptron. So, sorry, let me just make myself visible so you can see I'm here. So this might look familiar to you. This is basically the activation. So you take in all your features and multiply it by some kind of weight, and that's your activation, right? And then after that, you have to apply your activation function. And with your basic linear classifier, you can just quite simple. If your activation is, say, positive, you make it 1, the positive class. Otherwise, it's not the positive class. If it's 0 or negative. Cool. And of course, look at arbitrary, whether you want 0, 1, -1, +1. It's just whatever's convenient. The time being from a mathematical sort of coding point of view, whatever's easier. Now, one of the simpler things we can do is we can express our Boolean functions as a linear classifier. So that one's errored out. So our first one here is we want to express the OR function, right? The OR function looks like this. Right, so let's say this is x1, let's say x2, and then you'd have so and here this is 1 and 1. We assume 1 is true, right? So here, this is the field in circle means it's positive class. It's a positive class. So with all function, as long as there's a one of x or x is positive, then it satisfies the OR function. Whilst I may as well drop the AND function, right? And it'll look, just this, isn't it? And then AND function only spits out a positive class when both of them are positive. So back to Jupyter Notebook, we're trying to do this guy here. So this guy here is this guy here on the left. So that's our input, and of course you could plot this and you'll get what I just drew on the in the PowerPoint, right? Okay, so what do we want to do here is we're already given the weights. We're already given what weights will give us a good linear classifier, and the next thing we do is we just cycle through all the data. We're basically predicting, right? We're just cycling through all the data and running predictions, right? So what we do is cycle through all the end data points, and we initialize the activation. We start with the bias, and then we cycle through all the features and increment up, and then this will give us the the w.x, the sum product of the weights and the features. Okay, and then now that we've calculated our activation, of course, if it is positive, then we output 1. Otherwise, it is 0. And here's our prediction. So this is the OR function, remember? So the only time the OR is false is if they're both false. Otherwise, it is true, as we can see here. Next thing is, let's try the AND function. So the AND function should look like this. It only kicks in when both of them are positive. So yeah, we can see it's only kicking in here, 1 when both of them are positive here. So same thing, we're already given the weights here. We'll just loop through all the data points, right? And then this will calculate the activation. And this is the activation function of sorts. This is the activation function, the step function. And then we can see here that cycling through all the inputs, right? Our prediction is 1 here, and it's perfect, right? It's correct, right? This is the y, and this is the y hat, right? And this is these two functions are perfectly linearly separable, so there's no problems here at all. Now, The next thing we want to do is we want to consider using NumPy data structures to just speed things up and make things a bit cleaner and faster and nicer. One of the things we can do is instead of like using this for loop, we can actually just use a dot product, which we've seen a bit in the PowerPoint, right? So you can just dot your features and your weights instead of summing through them all. That one's a bit of a waste, right? Right. So let's do the same example, except let's do the exact same example, except we'll use some NumPy data structures to try and speed things up and make things a bit cleaner. Here's a data set. This is 0, 0, and that's the target. 0, 1 target, 1, 0 target, and this is the all function. So it's only false when x1, x2 are also false. So here are our weights, and this is the same as before. Cool. And then what we do now is we calculate the activations all at once. We do it all at once. We calculate the activations all at once and now this is a design matrix, right? So this is the design matrix, right? So this is all the observations. This is this guy here, all the observations, right? We do your matrix multiplication now, matrix multiplication of the weights and all the observations, and this will spit out a vector of length of dimensions n, or the number of data points, right? And then we have y hat, our score, and this is basically just you apply the sign function, and if it's positive you calculate positive, otherwise 0. Calculate the error, which is just the difference between the two. Then we can see here, look, here's our predictions, and the error is just when the y hat is different to the y, and which is not. These are the good weights. These weights were fine. The weights might look something. The weights might look something like this. Some like do the weights. If you plot it, it might look this might look something like that, right? Your and function, your or function, right? And if you use the weights from here, it might look something like that. Cool. Right, now the next thing. So we repeat this exercise, but we apply it to the and function, right? So again, so the first dimension here, each of these, that's an observation, right? Within each observation, it's feature 1, feature 2, target, feature 1, feature 2, target, etc., etc. We build up our design matrix, right? And we initialize our weights. Well, we know what the weights are. Well, it's been given to us. We set the weights, and then we calculate our activations for everything, and then we apply the sign function, and then look at the error. There we go. Activations, predictions, no misclassification. So remember, this is the and function, so it's only when x1, x2 are both 1 that we predict as 1, otherwise it will be 0. Cool. So the next thing we do is in the previous example we had the basic linear classifier, but the weights were given to us. Let's try and work out how to learn these weights. Let's make it a bit harder, right? Rather than learning the weights. Now, typically we initialize the weights to something small and close to 0, which is something which we'll do here, right? And there's a question here. Why must the inner dimensions of matrix multiplication, what must they be for the weight update? Now, basically in the algebra, for matrix multiplication to work, the inner dimensions has to be the same. So for example, if you matrix A times matrix B, the number of columns in matrix A must match the number of rows in matrix B. So that's fairly standard. Now it refers to an augmented data matrix here, n plus 1. The plus 1 is just the bias term. M is the number of features, and you have the bias term. Cool. Yes, transpose, blah, blah. Eta is a learning rate. Yeah, this class. Yeah. Okay. Now, another way we can go about doing our learning is, and you can see here, like we're gradually building up. We started with a for loop, and then we started using dot products, and now we're just trying to make it all matrixy to make things cleaner and more efficient and faster, right? So here, instead of cycling through the data and calculating the bumps one by one on each observation, what we can do is we can use a bit of matrix multiplication in order to do it all at once, right? So what we have here is we have first of all the eta, which is the learning rate, eta, which is the learning rate here, okay, and then we have our design matrix, right? We transpose it, so like before you transpose it, each row is an observation, right? And each column is the feature. You transpose it, right? And then what you have is each row is the feature and each column is observation, right? So then what you do is you go, so row one, so now you do this, and when you do the matrix multiplication, what you do is you multiply row one, which is effectively feature one, with all the times it's misclassified, and that will give you, and then when you multiply those two, then you effectively get a bump or nudge whenever it's misclassified, right? And you do the same thing across all the rows, and this will give you all the nudges and bumps and nudges you need at that iteration. So you just keep doing this, and this is a lot cleaner, isn't it? So instead of having the several for loops, you just have this matrix multiplication here to change everything. Okay. So now we put everything together, right? We have our data set again. You can uncomment it out to try the exclusive or and functions, right? So here it is. Okay. So and this is where we do the training with iterations. So before we actually we already knew the answer, but now we're saying, okay, no, we need to learn it. How do we do it? So this each iteration, what you do is you calculate. This is the activation using the current weights across all the data, all the data points, right? This y hat is the vector of predictions for all the data points, right? And then this updates the weight vector all at once, by going, this cycles through all the data and works out the bumps and nudges you need to the weight vector, right? You do that, and then you check the error, and the number of times you look at errors, which is when the prediction is not the same as the as the actuals, right? And then you see the number of errors with each iteration, and you can see here that after a few iterations it's pretty good. You stop getting all the errors with the AND function. Now that's all well and good, but let's try the exclusive OR function, which we know is not linearly separable. Let's see what happens. Yeah, there you go. So even if I set, so exclusive OR, you can't it doesn't work with a perceptron because it looks like this. Exclusive OR means like one or the other. So it's this guy or this guy. This guy is just not a thing. There is no way to draw some kind of line between them to perfectly separate them, which is why here, like in that example there, it's why the error is always a half. You just won't work with the basic linear perceptron. It's no good. That's something to think about. XOR, the exclusive OR. Cool. And this one here is we have this UCI diabetes data set, which looks like this. So these are all the features, and that's the target, right? I don't exactly know what each of these features are, but that's X1, say X2, X3, X4, X5, X6, X7, X8, and then this is the target, let's say. I don't really know what it kind of looks like, but obviously you can play around with data, have a look, what's going on, see if there's some kind of link between anything, right? Do I see anything? Yeah, so the target seems to be a lot higher in these lower ones. It seems to like, anyways, that's exploratory data analysis. You could probably do it in pandas. You should probably do it in pandas as well. As you've seen in the previous lectures, you can do some correlation heat maps. You can do some scatter plot matrices, do some plotting to get a feel of your data. But anyways, there's almost 800 data points, and there's 9 columns or 8 features and 1 target. Right. The next thing you do is let's test out our neural network. So, let's test out our perceptron. So we have our data set. We've already built up all the infrastructure from before, right? We do it for 20 iterations, okay? We again calculate all the activations for each of the observations in the data. Y hat is a score, right? And we apply, this is effectively our sign function. We make it 1 when it's greater than 0, else 0. Okay, and then here we calculate all our bumps and nudges all in one go, and we keep track of the error rate here and over time. So we can see that with each iteration, it's generally kind of getting better, but I think it's kind of stuck here. I don't think it's going to get much better after it's sort of just cycling round and round. It's not really getting much better. It's going 3, 4, 3, 8, 3, 5, 6, 5, 3, 4. Oh no, it's just 3, 5, 6, 4. Maybe I have more. I wonder. Let's add more iterations. yeah, no, it gets stuck. It gets stuck. I don't think we can get any lower than that, even if we increase the number of iterations, which is fine, I guess. Cool. The next, this is a bit of a extension. So I mean, I don't know if I'm supposed to cover it, but yeah, have a go in your own time. This is building up from your like basic linear perceptron into a multi-layer perceptron. So your artificial neural network rather than just the one perceptron. And then after this, you can apply it to your MNIST. Oh, not MNIST. This is like a sort of toy data set character recognition, right? 0, 1, 2, 3, 4, 5, 6, etc. And this is a neural network object which you can use to create a neural network. Yeah, have a play with this. I think this is a bit of extension. Cool. And then you can sort of experiment with this implementation with different learning rates, which is a hyperparameter. So in neural network learning, hyperparameter tuning is quite big. So you play around with all the hyperparameters and see which one will perform the best on your validation or test or cross-validation data set. Cool. So that's all we have for today, and I thank you for your time, and I hope you have a wonderful week. So thank you all, and I will see you next week. Goodbye.